All right, let's jump right in. Welcome to this explainer. Today we're unpacking a fascinating, completely invisible engineering problem that's happening right inside your smartphone. When mobile networks made that massive leap to 4G LTE, we unlocked incredible data speeds, right? It totally changed how we browse and stream. But that leap actually created a huge hidden headache for telecom engineers. How do you handle a traditional voice call on a network that was built exclusively for data? Well, the solutions they came up with are nothing short of brilliant.
Okay, let's dive into this roadmap. First, we'll look at the 4G voice dilemma. Then, circuit switched fallback, or CSFB. After that, we'll cover the 4 ways to fallback, explore the Volte solution, and finally, seamless SRVCC.
So starting with section 1, the 4G voice dilemma, data versus voice. To really grasp this dilemma, we have to look at what 4G actually is. When LTE rolled out, it was a huge, revolutionary step forward, but it was designed as a packet-switched network. That means it literally chops data into little packets and sends them over the internet. Traditional voice networks, like your older 2G and 3G, were circuit-switched. They established a dedicated, continuous electrical circuit between you and the person you were calling. So the multi-billion-dollar question for the industry was, if your phone is locked onto a 4G data-only network, how on earth does it ring when someone tries to call your old-school phone number? That brings us to Section 2, CSFB, or Circuit Switched Fallback. The engineers quickly realized that if 4G couldn't handle the voice circuit natively yet, well, they needed a trapdoor. Circuit-switched fallback is exactly that. It's a clever mechanism that tells your ultra-fast 4G smartphone to immediately drop down to the older, slower 3G network just to connect an incoming or outgoing voice call. And then, once you hang up, your phone climbs right back up to 4G. Now, what's really interesting about these authentic, on-the-ground engineering field notes is that they map out exactly how this technology is deployed. You can actually see the blend of technical English and Arabic here, showing the real-world planning of these fallback mechanisms. Near the top, under circuit-switched CSFB fallback, it clearly notes 4G down to 3G call. This isn't just some abstract theory. This is the literal blueprint engineers use to optimize networks out in the field. But here's the catch. Dropping a phone from 4G down to 3G takes time, and time is absolutely the enemy of a good user experience. If someone calls you and it takes 10 whole seconds for your phone to even start ringing, yeah, they're going to hang up. According to these exact engineering notes, 6.5 seconds is the critical time acceptance metric. If the network can execute that entire fallback maneuver in 6.5 seconds or less, it's considered a success. Anything longer and you're seriously risking a failed call. Moving to Section 3, ways to fall back, and how they actually meet that 6.5-second wire. Let's act as a bit of a translator for those field notes and rapidly break down the 4 flavors of CSFB. Number 1 is blind redirection. This is the fastest method. The network just kicks the phone down to 3G blindly, without even checking which specific 3G cell tower is best. It saves precious time, but honestly, it's a bit of a gamble. Number 2 is with measurement report. Here, the phone takes a quick moment to actually select the best 3G cell tower before making the jump. It's definitely more secure and reliable, but it does take a tiny bit longer. Number 3 is packet switch handover. This means not only does the voice call drop to 3G, but your background data session drops right down with it, so your apps don't entirely lose connection. And number 4 is RHII, or flash, which involves highly specific cell and frequency band selection. Engineers literally have to choose the right flavor for the right location to ensure they hit that 6.5-second time limit without sacrificing call quality. But let's be real, falling back to 3G was always just a temporary bridge. The industry needed a permanent fix. Section 4, the Volte solution. Eventually, engineers figured out how to make voice calls work natively on a packet-switched data network. They created Voice over LTE, or Volte. Instead of dropping down to an old 3G circuit, Volte packages your voice into tiny digital data packets and zips them over the 4G network right alongside your web browsing and streaming data. It was a total game changer. It eliminated the delay of the fallback, allowed for crystal clear high-definition voice quality, and meant you could actually stay on lightning-fast 4G while talking on the phone. However, Volte is incredibly demanding to set up. Looking back at the engineering notes, there's this strict trifecta of dependencies required just to make one Volte call happen. First, the cell site, the actual physical tower, must provide Volte capabilities. Second, the user's SIM card has to be provisioned for Volte. And third, the physical smartphone itself must support it. If even one single link in this three-part chain is missing, the Volte call fails, and the network is forced to use that old CSFB trapdoor to kick you back to 3G. Which leads us to the final hurdle, Section 5, Seamless SRVCC, Call Continuity. So picture this highly relatable scenario. You're driving in your car, you're on a flawless Volte call using the 4G network, and suddenly you drive right out of the 4G coverage area. The signal is dying. If you're entirely reliant on 4G data packets for your voice, your call is doomed, right? Well, the crucial point here is how the network steps in to save you from hanging up. They invented Single Radio Voice Call Continuity, or SRVCC. This is an incredibly sophisticated process that detects the exact moment your 4G signal is fading during an active call, and it dynamically triggers a handover to a 3G network. It literally packages up the active call, translates it from data packets back into a traditional circuit, and hands it off to the 3G tower. It acts exactly like a baton pass in a relay race. And when it's executed perfectly, you, the user, hear absolutely nothing. The conversation just continues seamlessly. Pointing back to our field notes for a second, we can see exactly how mathematically precise this baton pass has to be. Under the Volte section, the engineer mapped out the exact SRVCC trigger points. It says when RSRP threshold triggered while I'm in voice call and down to 3G. The network isn't just randomly guessing when to hand off the call. It is constantly, actively measuring your radio signal quality. Right there in the notes, you'll see the magic number, -111 dB. That is the exact mathematical threshold. As you drive further from the tower, your signal strength drops in decibels. The very moment your 4G signal strength hits exactly -111 dB, the network's internal alarms go off. It realizes you are about to drop the call, and it mathematically intervenes, triggering that SRVCC baton pass to step your call safely down to the 3G network before it's completely lost. It is truly amazing just how much complex engineering is happening behind the glass of our screens just to make a simple phone call work. So the next time you dial a number, I want you to think about this explainer. Will you notice that invisible 6.5-second fallback happening as your phone quietly drops to 3G? Or if you're out on a road trip, will you realize when you hit that exact -111 dB threshold and the network pulls off a flawless, seamless handover to save your conversation? Thank you so much for joining me on this one, and keep learning.